Hello students, welcome to the class of Digital Signal Processing. So today we will be discussing the inverse Z transform. We have already studied about the Z transform. We have studied different properties of Z transform. We have practiced several numerical questions on the Z transform. Now today we are going to start with the inverse Z transform. So first thing that comes in your mind is that it will be the opposite of Z transform, and that's very true. So what happened in Z transform was that a discrete time signal or sequence was given to you, and you took out the Z transform for that. Means the signal was given to you in the time domain, discrete time domain, and you converted it into the complex frequency domain. Now the signal will be given to you in the complex frequency domain, that is x of z will be given, and you will have to convert it to x of n. So basically there is a formula for the taking out the xn, but also along with that formula, since the formula is based on integration, complex integration. So to simplify the process of complex integration, we have four methods to calculate the inverse Z transform. So how we are going to do today is, first we will start with the introduction of the inverse Z transform. Then we will be doing the long division method, the four methods of calculating the inverse Z transform one by one. These are the long division method, partial fraction method, residue method, and the convolution method. We will be doing one example each, because without example, the theory of the method is not important. It's not going to be asked in the exam. We will be getting questions. And then once we complete these methods, we will be doing more questions in a different lecture. So let's get started with the introduction part. The process of finding the actual discrete time signal xn from its Z transform is called the inverse Z transform. So if I show it to you, then we were having this discrete time signal x of n. We were having this discrete time signal x of n, and we were calculating x of z. This was the time domain, discrete time domain signal. And we converted it into complex frequency domain. We converted it into complex frequency domain. Okay, now process will be the inverse of this. We will be having x of z, and we will be converting it into x of n. The formula to do this is xn is equal to xn is equal to 1 by 2 pi j closed integral over c x z into z to the power n minus 1 dz. Now, although the proof of this is not very important for your exam purpose, but let's do it very quickly. So for the proof, we start with the Z transform formula, which says x of z is equal to n is equals to minus infinity to infinity xn z to the power minus n. We change the variable n to k. So we'll write over here, let n is equals to k. Now we have this as x of z is equals to k equals to minus infinity to infinity x of k z to the power minus k. And we will take the summation of all the k and give it a name. So that was the thing that we have changed the variable over here. Now the second step, this was my first step. Now the second step over here is that I will be multiplying with z to the power n minus 1. As you can see over here, z to the power n minus 1 is there. So second thing that I will be doing is multiply with z to the power n minus 1. So x of z into z to the power n minus 1 is equals to k equals to minus infinity to infinity x of k z to the power minus k into z to the power n minus 1. So this becomes n minus 1 minus k. Now the third step is I'm going to integrate on both the sides. Now the third step is integrating both sides. Okay, so x of z to the power n minus 1 dz. And on this side also we'll be doing the same thing. Close integral over c xk z to the power n minus k minus 1. There was a summation also over here, k equals to minus infinity to infinity. Okay, and then you have this dz over here. Now, the very important thing for this one that you have to keep in mind, so that is related to the Cauchy's integral theorem. So, z to the power n minus 1 minus k dz. If I multiply this with what? 1 by 2 pi j, right? So if I multiply this one with 1 by 2 pi j, so how can I multiply? Only we cannot multiply, so we will have to multiply and divide both. So that we will be doing here. But first, let us understand. So this, at the value of this, at n is equal to k. If n becomes equals to k, then this becomes z to the power minus 1 dz, 1 by 2 pi j, and that will be equal to 1. And if n is not equal to k, so this is 1 when n is equal to k. And when n is not equal to k, that time the value is equal to 0. So using the same thing, I will rewrite it over here. On the left side we had x of z into z to the power n minus 1. On the right side, what we are going to do is we will multiply and divide by 2 pi j. So we had closed integral over here also. And then we had the summation k equals to minus infinity to infinity x of k z to the power n minus 1 minus k dz. N minus 1 minus k dz. Now if I change the order of this summation and integration, what I will be doing is 2 pi j summation x k equals to minus infinity to infinity, and this side closed integral, this is 1 by 2 pi j z to the power n minus 1 minus k dz. At k is equals to n, we can write this full thing as 1, and at k not equal to n, this is equal to 0. So now moving this 2 pi j over here, this side, we get 1 by 2 pi j closed integral xz into z to the power n minus 1 dz, and this side we had k equals to minus infinity to infinity x of k. So now this thing, when k equals to n, will become equal to x of n. So this is how you get the formula for the inverse Z transform. So this is not a very important question for a semester exam, but still we should know how did we get the formula. Now since the integration is complex, so we have 4 methods to actually find out x of n. This is a complex integration, and with the function xz being put over here, it can become even more complex. So we have certain methods. The first one among them is the long division method. So we'll be starting with the long division method in our next class. Thank you for keeping patient. Thank you. Let's meet in the next class.